midterm next Tuesday. There's a, in case you haven't found it, there's a sheet I posted that kind of like a review sheet, and now I realize that though we'll cover them today, items 7 and 8 won't be on midterm, and items 5, G, and H won't be. So you don't have to worry about those. Or F, or F, I'm thinking. I'll try and update this. For anyone who's either today or after next Tuesday, who like are struggling, apparently, in addition to the services the library provides, the math department has some kind of tutoring. I forget if it's either, I think it might be Wednesday afternoon, or Tuesday or Thursday afternoon. But it's something you can avail yourself to. You feel you will you. If you're new to San Francisco, this is the crazy weather we have. Summer, cold, rainy, you just never know. I hope that's not why we have all these absences. People on the beach, I guess. Okay. So we're gonna cover something called inverse differentiation today. That's finding the derivative of an inverse function. And for some of you, this may be a review, but I'm going to do a short little review of what an inverse function is. So if I had a function so what does this function do? It takes x, multiplies it by 2, and subtracts 1. So if I wanted to undo that, I could create a function. I use this notation. Now, just want to emphasize this minus 1 here is not an exponent. It does not mean 1 over f of x. It's the inverse. If I wanted to write 1 over f of x, I would write it this way. Be very clear about it. You'll find the same thing with trig functions. It can be a little confusing because if you see, well, that's the same as sine squared x. If you see sine inverse of x, you mean the inverse function. So, okay. So if I wanted to undo this, what would I do? Well, I subtract 1 from x, and divide it by 2. I've got an inverse function. I put some value in here. Let's say 1. So 2 plus 1 is 3. I plug that value in here. 3 minus 1. 2 divided by 2 is 1. To get back what I started with. what an inverse function does. It undoes whatever the function does. Now, let's just take a look at a very common function. Y equals x squared. And we wanted to look at its inverse. Well, its inverse is kind of this. As I said, inverse, not inverse function. Now, we have a little problem here because it's not a function. So sometimes to get a function to have an inverse, we have to restrict the domain. So if we take this function and we say, we're going to add this restriction that x is greater than or equal to 0. Now we're just looking at this function. And sure enough, it has a inverse, which also is a function. Just going to draw my artist's impression of square root of x. We walked in late. We're just talking for a few minutes about inverse functions. So that's a common thing we do with a function. Create an inverse, we restrict its domain. Another common example you run into trig functions. They're of course periodic. The inverse would have many results, but we create an inverse by restricting the domain. This would be the sine of x. And then we can have sine of x, domain, negative pi over 2. Now we can have an inverse function. I'm not sure if I can do this. It's going to look like that. Not very. You should be familiar with all this by now, but if not, keep this in mind. Since an inverse function undoes what a function does, if you switch their roles, start with the inverse function, the function will undo what the inverse function does. So if I were to say, let's say y of 4, right? So the square root of 4 is 2. I plug that into the original function, I get 4 back. Just undoes it. So we have a way of writing that, distinguishing something that is a function and its inverse. We say, if you compose the inverse function with the function, you just get back x. Likewise, you compose function, the inverse function, just a property of inverse functions. Now, one way to think of what an inverse function does, if you're looking at it graphically, is it takes some point x, y, and it converts it over to y, x. So every point on the function will have an associated point on the inverse function graph. And in fact, you can generalize this. You can say, if I have an inverse function, and I graph this is the line y equals x. And it's here too. You might be able to see that the inverse function is just a reflection across this line. That has to be the case because, as I say, we're switching x and y. Are there any questions about inverse functions before we move on? Seep in for a minute. So, if we want to talk about the derivative talk about the derivative of an inverse function. Particularly in terms of the derivative function. One might want to take a look at a graph to some arbitrary function. It kind of looks like this. And we'll pick some point on it and we'll draw a tangent. The tangent, of course, delta y over delta x, some m, which is the derivative of the function. Let's call this a point A. Well, if we were to draw the inverse function, not sure if that moves very well. Okay. There would be some equivalent point here which have a tangent. They're unfortunately a little too close. I think we're going to move A up a little bit. So this tangent is going to be delta y over delta x. function, the inverse function, well, the x's and y's are switched. So its slope is going to be delta x over delta y. That's the derivative at the inverse, the derivative of the inverse. Okay. Well, if you take a look at this thing for a second, that means it's going to be just the reciprocal of the derivative at a. And that's our key to inverse differentiation. I'm going to have a formula now. And we're going to write it pretty much just like this. Function. I want to find its derivative. And I know the derivative of the function. And they're reciprocals. It's going to turn out to be more useful to write this in Leibniz notation. So the inverse function, that's the function I get if I solve for x instead of y and find the derivative in terms of y, or dx dy. That's just going to be the reciprocal of my normal derivative of y dx. Now, for those inclined, there's a proof of this, or a derivation of this in the book you can look up. I think it's actually in the appendix, using our definition of derivative. Of x is, I don't think I'm going to ask for this on the test. You should all have this pretty burned in at this point. Limit as h approaches 0, this limit. There's a proof of this. It's just kind of onerous and I don't think very useful at this level. What would be useful is some kind of example. So let's take a look at how this might work with the function we were talking about, y equals x squared. So we know that dy dx is going to be equal to 2x. But what we want to know is, we want to know the derivative y equals square root of x. Well, we already know that. We already can figure it out. We're just trying to see an example to see that this makes sense. So our formula says dx dy is equal to 1 over dy dx is 1 over 2x. But we're looking for a y here. We're looking for an x in terms of a y. Well, we can use this here. If y is equal to x squared, then x equals the square root of y. So this is equal to 1 over 2 square root of y. Well, I'm saying is derivative y, square root of y, is 1 over 2 squared y, which we already know from the power rule. But you can see this is one way to get an inverse function, the derivative of an inverse function. This was not very useful though, because we already knew it. So let's take a look at an example that might be useful. You look at the function y equals dx. So our inverse function is, of course, y equals the natural log of x, or if you like writing it this way, log to the base e of x. Just curious, does anyone here already know the derivative of log of x, the natural log? Don't shout it out, I'm just curious. You haven't run into this before. Well, okay, so y dx is what? Someone who's had their coffee and feeling awake and not too shy. Thank you. It's e to the x. That should be like 1 plus 1 equals 2 by now, right? All right, so the x, y, is going to equal 1 over y dx. And that's just equal to 1 over dx. What does e to the x equal? That tells us that we have x equals y. X prime is equal to 1 over y, or as we probably more likely write it, y equals 1 over x. That looks pretty useful. I want to digress for a second here because there's something that this fits in somewhere that I think is really nice. You won't need it until much later in the class. I'll mention it again. But if we were to look at the power rule, of course it's n x to n minus 1. Let's look at just some examples. So, derivative of x cubed is 3x squared. X squared is 2x. Derivative of x is 1. Derivative of x to the minus 1 is -1 x to the minus 2, and derivative of x to the minus 2, -2 x to the minus 3. Okay, so ignore the constants for a second. see? We see a pattern. X squared, x to the 1. This is x to the 0, x to the minus 2, x to the minus 3. We skipped one, didn't we? We skipped x to the minus 1. Interesting. We found it. We found where that goes. It's the derivative of the log of x. So it's an interesting point to note that it kind of fits in here somehow. If I wanted to go in the other direction, I wanted an inverse power rule. Well, I can reverse this until I get to x to the minus 1. And something interesting happens, something kind of funny. Okay. Any questions on that? Why don't we just try derivative right now? Try this derivative. X times the natural log of x. Try to give it a shot. Take a minute or two. All right, so how do I go about this? What's the first thing I have to try here? Yes?
Use a product.
Product rule. Everybody see that? It's kind of the product of two functions we know. So it'll be x times the derivative of log of x plus log of x times x. Okay? Well, now we know what the log of x is. Oh, it's just 1. And that's 1. we made it a little harder. We'll say x to the n is the log of x. No way, n is, yeah, that's not an impediment, is it? Look at that. Right. These are coming a little easier now than when we started. Does someone have a solution for me?
That would be x to the n minus 1 times the n times the natural log of x plus 1 in parentheses.
That? I haven't figured it out, so someone else tell me, does that look right? Okay. Not too bad. All right, so this is two new tools here. We've got this inverse function rule. Dx dy equals 1 over dy dx. And now we know the derivative of the log of x, the natural log. I'm going to show you my own vulnerability here. You said, what was the natural log of the base 10 of x? How would I know how I figured that out? I'm not asking for the answer. How would you figure that out? Ideas here? Well, we learned about logs in pre-calc, right? There was a formula, right? Log to the base A d equals log to the base C of d times some constant. Remember the constant? I don't remember the constant. It's a change of base rule, but some constant. Let's call it C. So I know that there's some constant, right? I have to find that constant. The derivative is just going to be that, right? This is like, to me, this is like one of the hardest things to remember from one year to the next. It's either going to be either log to the base A of C or log to the base C, and I forget which. All right, so this is pretty powerful. We not only know limit x, we can, for some arbitrary base, we can find out. You could use the same strategy if you want to find the derivative of this. We change the base, we change it to e to the x, so we know what the derivative of that is. All right. Let's use this. Let's use this to do something not so easy, but useful. So what I want to know is, what is the derivative of the inverse sine of x? And I'm gonna use this same strategy here. First, I want the derivative of my function. I know that. Again, it should be like 1 plus 2 equals 3 by now. Derivative of the sine. The cosine. So x dy equals to over the cosine of x. But I want this in terms of y. You know what? I know how to do that. Do I know how to do that? I know what y is, sine of x. Now I have to figure out the cosine in terms of the sine. Anyone remember how to do that? I think you all know this. Is that going to help me any? 1 minus, sorry. Starting to see a pattern here, but I don't think we're quite there. What's that? That's sine of x. Sine squared of x. Oh wait, I don't really care what the sine of x is. I want to do it the other way.
You square root both sides?
That cosine of x equals
good. Ah, now I can substitute here. So it turns out the derivative of the inverse sine is 1 over square root of minus x.
On the, like, midterm, would you expect us to, will you like say, put it in terms of y? Or would it be okay to just leave it as 1 over cosine x?
Well, I don't think this is very useful the way it is, right? If you're just calculating a value, it would be useful. Yeah. Plug in the cosine of x. Love that phrase, if it were on. Must be very careful because I haven't written the midterm yet.
Oh, okay, now.
Now you will be pelted after class by your Steve's got a photo of All right, kidding aside. Let's do another one. Let's do another one. Not very different. We know what the inverse sine is. We might as well learn what the inverse cosine is. I think this is going to go almost the same. So the derivative of the cosine is I can barely hear murmuring in the back. Everyone?
Negative sine x.
Negative sine. Right on the football field. What's the derivative of the sine? Everybody's gonna yell, right? But not in here. Okay, so dx dy is negative 1 over the sine of x. But we're going to convert that into a cosine, right? It's going to be what? All at once. All right. 1 minus cosine squared of x. So minus 1 over minus x squared. So it turns out that the cosine, the inverse cosine of x, is derivative, is just the negative of 1 over the square root of minus x squared. Well, given that we didn't have to go through the pain of saying cosine inverse x equals the limit h goes to 0, cosine inverse of x plus h minus cosine inverse of x over h. We didn't have to do that, right? Of course, now we know this is true. There's just a little, that'll come up anywhere. It will come up. Probably on the first A in a weird kind of way. Yeah, so if we know the derivative, we know this limit. Right? All right, we're almost done with the trig functions here. For now. these are the important ones. Sine and cosine and tangent. All right. What's my next step here? What do we want to go here? Modeling. What's my first step? I'm going to use this formula. It's going to tell me the derivative of the inverse tan in terms of the derivative of the tan, so I have to know the derivative of the tangent. Oh. Now, again, something valuable to know by heart. Figure it out knowing derivative of the sine and the cosine and the quotient rule. But this is a good one to know just like that. Anyone recall the derivative of the tangent?
Oh, no, you're good. Secant squared. Secant squared.
Secant squared x. Okay, so that tells me my dx dy equals 1 over the secant squared x. Which is actually cosine squared x. But to follow through in what I'm doing, I need the cosine squared. I need to connect the cosine squared and the tangent. We have to again rely on our encyclopedic knowledge of our pre-calculus trick. All right, not everybody remembers this thing. Pythagorean identity just comes in useful all over the place. Are you fine here? Okay. This would have been useful to have burned into your memory. Looks like it's 1 over tangent squared plus 1. Happy with that? So my last step is just tangent squared. Where's that? Is y squared. So, you can forget in all this what we're trying to find. We're trying to find the derivative of the inverse tangent. And that's 1 over x squared plus 1. right. 3 very useful derivatives that probably commit to memory for duration. Be helpful. Okay, it's time for a break. Comment about homework. First, to those of you turning in homework, appreciate it. Good. I'll, of course, get it back to you as quickly as I can. The homework does not have a huge percent of the grade, but it's important. If you've taken the class already and you know stuff, no big deal. But if you're not getting practice here, you're going to find the midterm difficult as the rest of the class. So I'd like to encourage, I accept late homework. I encourage anyone who hasn't checked out to do their best.
Professor, you had an announcement on Canvas that you posted the midterm review sheet, but like a bunch of us couldn't find it. So we were wondering where it went.
I'm sorry, you couldn't find it?
Yeah.
It was just an announcement, there was no attachment.
It's a page.
There is.
Can you look at the,
There isn't.
I'm new to Canvas, and maybe I'm not doing things quite.
In pages.
Oh.
You click pages, it's in pages.
Take a look.
Oh, thank you.
I don't know if anyone else is having trouble. I tried to log on this morning and I couldn't. Okay, there you are.
Oh.
Look under all pages.
I was like there, and I had
Thank you.
Okay. If you think there's a better place for me to put such things, let me know, because, like I said, I'm a little new to this.
Professor,
Yeah.
I know you haven't written the midterm yet, but do you think there'll be more than 20 questions?
I'm sorry, I'm not hearing you over the air noise. Yes?
Do you think that there'll be more than 20 questions on the midterm?
Do I think there will be more than 20 questions on the midterm? No, I don't think there will be more than 20. But as reasonable as that question sounds, 40 really simple questions would be a lot easier than, say, 5 really hard questions, right? So I wouldn't worry about the numbers. Let me then take a break here for a second and say something about exams. You're only going to get 3 exams here. You're going to get 2 midterms and a final. And that tends to make things feel kind of high stakes. That's unavoidable, but being calm about things is not. If you've done the homework, you've come to class, if you don't feel like you're not understanding anything I'm saying here, you're probably going to do okay. I don't write the exams to try and trip people up. If it's a really, really hard question on the exam, it's probably an extra credit. You don't have to do that anyway. Again, I try and balance the exam so I get to see that you know the subject we've covered, of which there are numerous, but at the same time, I don't want to make it kind of a time thing where you feel pressured for time. If anyone feels like after the exam that, hey, I could have done better if I had more time, I will be very surprised. I've been doing this a long time, and honestly, if after the class, if you have time and after the exam, after the class is over and you still feel like you want to spend more time on it, I will allow that. It's not my intention to make math a race. Say, show me that you know how to do the problems. So I would worry less about that. I would also, again, I'm sure some of you I'm speaking to the choir here, but get a good night's sleep the night before. Don't stay up till 2 in the morning studying. You're going to be worse off unless you didn't study at all, and then you're in trouble anyway. Come alert and don't come knowing that you did the studying, you did the work, and you'll probably do okay. Don't talk yourself into a panic. That doesn't help. It's like being on some athletic team and talking yourself into psyching yourself out, right? That's the other team's job, right? Not yours. And it's not my job either. Okay, we're gonna having developed some tools here. Well, I didn't write it down. I guess I'll put it back again. This would fit in nicely right here. Derivative of log of x, 1 over x. Using this and our previous subject, implicit differentiation. I'd like to have a quick review on that. If I have some description of a curve, an equation like x cubed plus y squared equals xy. And I want to know, I don't have y explicitly in terms of x. I don't have, I can't really solve this. But I do want to know what y prime is. I want to know what y prime is maybe in terms of x and y. I can do that with implicit differentiation. And here's how I go about it. I'm going to find the derivative of both sides with respect to x. So 3x squared, that's just 3x cubed, that's just 3x squared. In the case of y, I treat y as a function of x. So it's 2y, and now using the chain rule, times the derivative of y. Again, if you want to put in little x's here, that helps. This side I have the product, so I use the product rule. X times the derivative of y, is y times the derivative of x, that's y. So now, this y prime is what I want, so I'm going to solve for it. So I'll 2y, y prime minus y prime equals y minus x cubed. I move this over there, move this over here. I factor out my y prime. And I divide, and I get the result as before. Okay, this is implicit differentiation. It says that we don't have to know y explicitly in terms of x to find the derivative. Yes?
Should the x cubed be the 3x squared?
Yes, I see. my right hand doesn't, it got a C in calculus. I'm fine, but gave up bringing the couples to class, but if you want to come down to the office and code one. Okay. Question about implicit differentiation. We're going to just find this beautiful use of it. All right. So the technique here is called logarithmic differentiation. Don't worry about what that means. It's much simpler than what it sounds like. Let's do an example. Let's start with an example that we wouldn't normally do this way. Y is equal to, say, x squared plus x plus 1 over x. So it'd be much easier to just divide through by x and find the derivative of the sum. Instead, we're going to go around the long way and see how this works. We're going to start by finding the log of both sides, natural log of course. Now, using the properties of logs, which you should all remember, this is the log of x squared plus x plus 1 minus natural log of x. Okay. Now we're going to find the derivative of both sides, just like we did when we were doing implicit differentiation. Derivative of the natural log of y, that's just going to be 1 over y times the derivative of y. I'm going to pause here for a second. If I have some function f of x, I want to find the log of it, and I want to find its derivative, I'm just going to use the chain rule. It's just going to be 1 over f of x times, the chain rule tells me, times the derivative of f of x. The 1 over just comes from the derivative of the log of x, right? I'm composing these two functions. That's all I'm saying here. Derivative of the log of y, which is a function of x, is just 1 over y, derivative of y. Right? Now I want to find the derivative of the log of x squared plus x plus 1. Well, again, it's just going to be 1 over x squared plus x plus 1. And we've got a composition of functions. The chain rule requires I multiply by the derivative of this, which is 2x plus 1. And I already know the derivative of the log of x. Okay. Well, let me write that a little more. That's 2x plus 1, or x squared plus x plus 1 minus 1 over x. Combine, it doesn't matter. Well, what I want to do here now is I want to multiply through by y. That's my derivative. But I'm not quite done, because I really want this whole thing in terms of x. So that just becomes 2x plus
squared plus 1 is 1 over x times, well, what was y? Oh, I know y. Y is x squared plus x plus 1 over x. This example is here just to show you how you do it. It's not really the way you should do this. You'd be better off using the product rule. You don't even have to do that. Since this is x plus 1 plus 1 over x, the derivative is just going to be 1 plus 0 plus negative 1 over x squared. So, you know, I'm like saying, you telling me all this is that? Yeah. I don't really want to work it out. So why would I do this? Why would I use this? Well, obviously not in this example. Anyone's still writing down? Okay. Let's look at an example where logarithmic differentiation is useful. Not required, but useful. This is an example from the book. Evil. I wanted to make a point. Yeah. Now, not necessary. We could use the product rule, and there's a power rule, and another power rule, and a product rule, another power rule. We could do this. If you want to check my work as an exercise, go right ahead. Let's see how the logarithmic differentiation helps. Find the log of y. And I'm just going to, I'll write it all out so we don't get lost. All right, that's the log of x to the 3/4 plus the log of, I'm going to write this as to the half power, right? It's going to be helpful in a minute. Minus log of 3x plus 2 5th. Okay, we're going to see how I use the, rules of logs, right? Log of a plus k times b is log of a plus b. Log of a divided by b, log of a minus b. Okay, but here I have a power which can go over here. Now we're going to find the derivative of both sides. We're going to find doing that much easier than it would have been here. So again, I have 1 over y. I'm just going to write this y prime over y. And 3/4 derivative of the log of x is just 1 over x. One half x squared plus 1, right? 1 over this, but now I have to use the chain rule here, so times 2x. It's nice, that's going to cancel.
cancel.
Minus 5 times 1 over 3x plus 2. Well, again, I have to use the chain rule, but that just introduces a factor of 3. All right, let's at least rewrite this.
Wait, I'm sorry. Can you
Sure.
explain the G rule part again for this?
Okay. This is a composition of functions. The log times this.
Yeah.
So it's the derivative of this function at this function. That's 1 over x squared plus 1 times the derivative of this.
Okay. Oh, okay, so you just did that. Okay. That makes sense. Yeah, yeah.
And thank you for slowing me down.
No, I just, it
No,
just
no.
blew right past me. so-
No, thank you, because I don't know when I'm blowing past people, and that's your job, students. Stop me. It's not rude. It's not impolite. X over x squared plus 1 and minus 15 over 3x plus 2. I'm going to cheat here. I'm just going to multiply by y. So y, oh, there it is. That ugly mess. 3/4 x squared plus 1 over 3x plus 2. Now, you might have kind of a knee-jerk reaction to try to simplify this. In some cases, that might be worthwhile. It doesn't look very worthwhile here. I mean, we have no common factors here, and then we have this ugly thing. It's not going to look much better if I try and simplify it. However, if I ask a question like, what is y prime of 1? Wow. This isn't going to be very hard at all. Okay? No big deal. You might be asked a question like that in these terms. You might be asked, given this function, you know, tell me the equation of the tangent in 1. Okay, y equals mx is x plus b. Now I just have to plug in 1 here, find out, right? 1, let's see, 1 square root of 2, try to figure out what y is. Square root of 2 over 5 to the 5th. Now I can find out b. Y equals x plus square root of 2 over 5 to the 5th minus 1. That's my tangent. So, I mean, you know, it could be a much uglier number, much more complicated, and designed to panic you on an exam, but again, that's not my philosophy. I'm not trying to kill you with numbers. Okay. As I said, that's an example where, yes.
I'm a little confused about after
Lillian, I apologize, your voice is barely above the air currents up here. Imagine you're in your rhetoric class and speaking before everyone. Speak from your thoracic area. Try again.
My question is, after finding the y prime, why did you multiply the y, like the whole y value again?
Ah, okay, I hid that from you, huh? Okay, let's go back. I had here the log of y, and I found its derivative, which is y prime over y. You got that part? Ah, let's try again. So that's very key here. I don't think I'll need this. Let's erase this here. I have y equals some function of x. I find the log of y. I want to find the derivative of both sides. Now, y is some function of x, right? Just call it y of x. So I'm going to use the chain rule because this is a composition of functions, the log and y of x. I'll write that down. Derivative of f of g of x is equal to the derivative of f at g times the derivative of g of x. Okay? So we're gonna replace this here. F here is the log and g is the y. So this tells me that the derivative of the log of x at y of x. The derivative of the log of x. It's 1 over x. So it's 1 over x at this, at that function, times the derivative of y at x. I realize it might be tricky to see this, so don't give up. Just keep looking at it. This is something we do a lot in implicit differentiation. We take our y, we don't know what y is in terms of x. But we just make believe we do. We call it y of x. And we find its derivative. It's y prime of x. Here, since I've got the log of y, well, now I have to use the chain rule. 1 over y times the derivative of y. So that's how I end up with this y prime over y equals, let's just fill in log of x to the 3/4 square root of x squared plus 1, 3x plus 2 5th. Find the derivative of this, which I can do using, breaking it up using the log, the laws of logs. So that's the first part. The next part, maybe this makes sense now. Since I have y prime over y is equal to, oh wait. I'm not calling this you either want to try and figure it out, or you want to try and come ask me after class. This is important. You need to be able to do this. Not for the midterm. You will need to do this. Okay, so you see where I am here? I have y prime over y, but I know what y is. I can multiply by y. Y is just where I started. So just fill in here all that other x stuff. Okay, I want everyone happy with this before I move on. We're going to do something I think is kind of beautiful, it's kind of creative with this. And it's actually less board space. Any questions? All right. Action-packed day in calculus here. So, let me write a function you probably haven't seen much. Does anyone know the rule for finding the derivative of x to the x? Anyone want to guess? There is no rule. I don't know any rule. It doesn't look that new, but it doesn't. Can I use like x times x to the x? No. Now, that's not how the power rule works. It needs a constant, any constant. This is not a constant. This is what I love about this technique. We're going to use it, we're going to solve this, and it kind of feels a little like, like a magic show. Nothing up my sleeve, nothing in this box, and I'm going to pull a rabbit out of it. Okay, if you paid attention last time, this is going to be easy, but it's just so beautiful that it comes out the way it is. I don't know how to find the derivative. But I'm just going to try this log thing. Okay, so I know from my logs that this right? Okay, let's find the derivative of both sides. Once again, this is just 1 over y times y prime. Okay, what do I need to find the derivative here? This looks awfully familiar, doesn't it?
Yeah, the power rule.
Well, yeah,
Or not the power rule, sorry, the product rule.
probably, yeah, but we did this earlier, didn't we? Yeah, it wasn't that hard, was it?
No.
Okay, so it's x times log of x plus log, x times the derivative of log, which is x, plus log of x times the derivative of x is 1. 1 plus log of x. So I have y prime over y equals 1 plus log of x. What do I do next? at y. Oh, I know what y is. Y is x to the x. Oh, wow. You know, once you get this technique, this is just like, oh, 1, 2, 3, 4 lines, and you probably could do it in less. But really, sometimes logarithmic differentiation can be really powerful. All right, I have great confidence in you people. I'm going to let you loose on something. Give this a try. Be brave. Just, all right, looks terrible, but you've seen it done. Let's give it a try. Curious what this looks like. You know, whenever you get to pi, or a factor of pi, it's going to be 1. Sign is going to be 0. But I don't know what it does. Oh, at some point it was negative. I will get a Ismos in my office later. Anyone have a solution? You know what this is? Someone? Juggling, you know, you practice it a little and it's not too bad. Okay, there's something I wanted to say before I let Oh, yes, I want to say, the homework assignment for this week, for the stuff we do this week, I'm making it due on Thursday, not Tuesday, not that it matters that much. I just want you to not feel like you have to focus on this. That's it. Have a good afternoon.